So first, uh, first we'll do this current density. Now this is a new term. Current density is a new term, a new concept that it has never been taught to you in your junior classes. Now to understand current density, you have to understand that some two concept you have to understand first. You have to understand that if this is the area, so you have to have an area vector, isn't it? So the concept of area vector is already known to you. You have done this in the previous chapters. Now, if there is a conductor, and again in the conductor you have a specific, you have decided that this is the area you want to focus on, then this area will have some area vector, vector which is perpendicular to area. So current density will be is equal to the charge passing through this area. If you read the definition, proper definition, the current density at any point inside the conductor defined as the amount of charge flowing per second through a unit area. Again, this unit area, the amount of charge flowing, that is the positive charge. Let's say this positive charge is flowing. Okay, so how much this of amount of charge is flowing through a unit area held normal to the direction of the flow of charge. So you see this area is held normal. This area is held normal. Now don't confuse this, that this is normal, but this is area vector. This red line here is area vector. This is area vector, and this is the area itself. So in the definition it is given the unit area held normal to the direction of the flow of charge. So this is your direction of flow of charge, and this unit area is held normal. Okay, so this is what the definition is, that amount of large charge flowing per unit time this through this area. And it is a vector quantity because this also have a direction, okay, having a same direction as the motion of the positive charge, having the same direction as the motion of positive charge, and it is denoted by this J. So current density will become J, okay, J with a vector sign on the top, because this is the vector. Now J will be is equal to I by area. This value here J will be is equal to I by area, or current over time by area. Now if this area is not perpendicular, what if this area is not perpendicular? So if it is not perpendicular, then we have to take a component of this area. Let's say this is your condition. This area is not perpendicular to the flow of current. You see, this area is not perpendicular to the flow of current. So current flow is here, area is here, area vector is here. Okay, so then what we have to do, we have to do the cost component of the area. Instead of area A, we will have to take A cos theta. Okay, we'll have to take A cos theta. So J, current density J was I over A, but instead of A, we have to take A cos theta. Now A cos theta, you see A was a vector. Okay, A is a vector. This is area vector. You see, this is area vector. Now if you rearrange the expression, it will become J A cos theta. That is also is equal to J dot A. That is the current density dot the area vector. That means these two value will be is equal to I. These two values is equal to I. So I is current. You can say that the current is the scalar product. You see, electric current being scalar product of two vector. Okay, and it's a scalar quantity. We know this current is a scalar. and the scalar product of two vectors here, j dot a, will produce the scalar value. So current is the scalar product of two vectors, and two vectors means current density j and area vector a. The SI unit of current density, very simple. SI unit of current density will be ampere per meter square. The next topic is conductance. What is conductance? So we have understood what is resistance. So conductance would be just the reciprocal of resistance. So if this is, if the conductance is equal to reciprocal of resistance, if an object has lower resistance, that means it will have higher conductance. Okay, very simple. So conductance SI unit will be inverse rho, ohms inverse ohms, okay, or Siemens. Then you have conductivity. As you have resistivity, so you will have conductivity. That is also simple. Conductivity is equal to 1 over resistivity. And these are the SI unit, inverse ohms, inverse meter. Then we come to something called vector form of Ohm's law. Vector form of Ohm's law. Now from the potential gradient formula, you already know this. So potential gradient delta V is equal to E dot dr, you can say delta R, or you can change this expression a bit. You can just say, okay, potential is equal to the electric field times the length of the conductor. If you're considering in the case of a conductor, then R would become the length of the conductor itself, and then you can find the potential difference between these 2 points. So basically you can just put EV is equal to E into L. Now, if V is equal to E into L, but V is equal to I into R also, that also you know, I into R. And R is equal to rho L by A. So you're going to just equate these two values. E into L is equal to I rho L by A. E into L is equal to I rho L by A. L cancels out. And then E is equal to J into rho. What is E? E is the electric field. What is J? Current density. What is rho? Resistivity. So electric field will be is equal to resistivity, current density, and these two, electric field and current density, are vectors. So J is equal to conductivity, because 1 over resistivity is conductivity. So if you rearrange the equation, it will come in the denominator, it will become conductivity into the electric field, and this is called the vector form of Ohm's law. It is equivalent to the V is equal to IR. Okay, vector form of Ohm's law. Now, classification in the terms of classification of material. Different materials can be classified as a conductor, insulator, or semiconductor. Now, conductors, insulators, and semiconductors. So, the standard definition, if the resistance is very high, then it is obviously not a conductor. If the resistance is low, then it will be a conductor. So like that, you can very easily identify the materials which conduct electric current fairly well are called conductor. You can pause the video and read this whole thing. Basically, the main thing you have to remember is this value here. Okay, they have the low resistivity, 10 raised to minus 8, ohms per meter to 10 raised to minus 6. Okay, need to remember this value here. You can read this thing. And then you have insulators which have the resistivity of 10 raised to 4. Okay, and semiconductors are those which have their resistivity lie between those two conductors and insulators. That means these two values. Okay, these two values. So this will become how much? 10 raised to minus 6 to 10 raised to 4. More about semiconductors you will learn in the further syllabus. Now next topic is color coding of carbon resistors. But let's first discuss about the different types of resistors. In your book also you will find different resistors. Carbon resistor is one of the one which is used mostly. You can just do a simple search, Google search, find out carbon resistors, you will find it. And okay, just wait, let me put it. So this is what carbon resistor looks like. If you focus here, this thing here, not this one. Yeah, if you focus here, then you see that these are colors. You see they're different colors, and there are 4 bands of color. If you look closely, 4 bands, 1, 2, 3, 4. Every resistor will have 4 bands of colors, and the band color is not same also. Okay, the different colors. So here you have 3 reds, you have 2 browns, a black in between, and so on. Okay, so this is what we have to understand. This is pretty simple. So you can read the basic definition of the carbon resistors, and they have certain advantage of carbon resistor as well. You can pause the video and read these things. So color coding. First, you need to understand a numbers that is correspond to certain colors. Every color has been given a particular number. So black has been given a number 0. Brown is 1. Red is 2. Orange, yellow, green, blue, violet, gray, white. Every number is given, every color is given a number. Now, when you see a register, your register will look like this. It's raw register, carbon register. So this carbon register has colors like this. Okay, so this is the first color in the register, and then you have another color here, blue, and then you have another color here, brown. Okay, and there might be another color here as golden. So the first color that you see, okay, this color here, this is red. So what you have to do, go to the chart and see what does the red color correspond to, which number. It corresponds to number 2. So the value of 2 will be taken first, 2. Then find out which is the second color. The color is blue. So what is blue? Blue is 6. So the next digit will become 6, 2, 6. And find what is the third color. So third color is brown. What is brown? Brown is, you see this, brown is 1. That means the third digit will come as a power of 10. This is the first color digit, second color digit, but the third color digit will come as a power of 10. The fourth color is is gold, silver, mostly gold or silver. This does not represent any number of the resistance. It only represent the efficiency. How good is the resistance? If the resistance is good, that means the manufacturing is very good, and you have bought like good company, nice branded resistance you have bought. That means it will be very efficient. That means the tolerance level, if it is gold in color, then the tolerance level will be plus minus 5%. That means the value which is specified will fluctuate from the actual value to plus minus 5%. And if it is silver, then this will fluctuate to plus minus 10%. So that is what your carbon coding is. Do practice some questions. It's a very simple topic. Now there is a fair chance of you will forget this numbers related to the colors. So there is a jingle here. You will find this particularly in every book, and it's pretty easy to remember. So BB Roy, this is jingle is BB Roy. So BB is the first two colors, that is BB's, B becomes black and brown. ROY, red, orange, yellow. Okay, BB Roy of Great Britain. So GB, Great Britain's GB. BB Roy of Great Britain, GBG is 5, that is green. Okay, and B is blue. And V is violet. Okay, V is violet. Had good wife. So G again will gray, and wife W is white. So B.B. Roy of Great Britain had very good wife. So when you learn this pretty easy jingle, you will remember it. B.B. Roy of Great Britain had very good wife. But in this jingle again, there is I have experienced students making mistake with this BB and this B. There are three different B in the this one. So do remember that the first B is black, the second is brown, and the third is blue. So black, brown, blue. Okay, so I have known student who somehow in the exam think that this is blue. Okay, so don't make that mistake.